Warami, everyone. This means hello, Warami, or where are you from in Darug Talang, the language of the local Aboriginal people. I begin by acknowledging the traditional custodians of the land on which we meet tonight, the Wallumattagal clan of the Darug Nation. Their rich cultures and customs have cared for and sustained this land since the Dreamtime and continue to do so today. We pay our deepest respect to elders past and present, and I also extend this respect to all First Nations people joining us this evening. The First Nations people really are the original scientists, engineers, and innovators on this land, custodians of knowledge spanning tens of thousands of years. Welcome to another installment of the Discover Public Lecture Series, proudly hosted by the Faculty of Science and Engineering here at Macquarie University. If this is your first time attending this lecture series, a warm welcome, but I also see so many familiar faces, so a warm welcome back to everyone who enjoys this particular series. I'm Professor Samuel Muller, and I have the privilege of being the Executive Dean of the Faculty of Science and Engineering here. Let me say a few words about the Discover Lecture Series, particularly to those of you who are here for the first time. This is now the second year that we offer this series. The theme is built around the words discover, create, innovate, as you possibly have noticed outside with the sign that is up. And these reflect really our mission to expand understanding, transform knowledge into real-world solutions, and shape the future. And I want to give you one example against each of those three words of our tagline. In terms of discovery, our astronomers produce some amazing work. Today, one of our astronomers / data scientists showed me 2 images that will be published tomorrow, so I can't really tell you what is on those images. But it's absolutely awesome what is currently discovered by the wonderful technology that is available. In terms of creation, our applied bioscientists in our faculty are working to protect Australian crops by tackling, for example, the Queensland fruit fly, which is a major agricultural threat. In terms of innovation, well, we are here tonight to hear a lot about innovation, turning bold ideas into technology that change lives, industries, and futures. So let me introduce Professor Michael Boers, who is tonight's distinguished speaker. He's an industry professor here with us at Macquarie University. Mike is the founder and chief technical officer of Atto Devices, a fabulous semiconductor company. Now, when I read this term fabless, I noticed before I looked it up what it means. I actually don't know what it means. So by a show of hands, who felt exactly the same way as I when I read the term fabless? So anyone who hasn't their hand up can explain what fabless means. Mike, do you volunteer?
Draw pictures of the chip instead of printing it. Somebody else does the printing.
Excellent, excellent. So we'll leave it at that. I'm not going to come up with a different explanation, even though there's a slightly different explanation right here. This Mike, not that Mike, specializes in advanced hardware systems and silicon microchip design for wireless communications, sensing, and biotechnology. His impressive career includes leadership roles at Broadcom, Movandi, and CSRO spin-out QuasarSat, both in Australia and the US. He holds an electronics degree from the University of Sydney and a PhD from our own university here at Macquarie. Mike is also a passionate advocate for strengthening Australia's footprint in the global semiconductor sector. We are truly fortunate to have you, Mike, here, along with your team, or part of your team, your vision, and your entrepreneurial spirit. So now it is my great pleasure to hand over to you, and you're going to present tonight's lecture on From Sand to Circuits, How Microchips Shape Our World. Once again, welcome all, and thank you for being here.
Wow, well, thank you everyone for coming. It's so nice to see you all here at Macquarie Uni on a windy and cold night, so really appreciate that. And what I'd like to do for the next 40 minutes is talk to you about microchips. Now, microchips are the fundamental building blocks of all advanced technology. They're inside your mobile phones, they're inside your cars. And the story of microchips is really a story of compounding growth in the fantastically advanced factories called foundries that manufacture these chips, but also the story of design and innovation in wireless and sensing and computing technology that we rely on today. Now, to understand how critical microchips are in the 21st century is to understand how important oil was in the 20th century. Countries that control the design, the manufacturing, and the end use of microchips continue to be the most economically complex societies, as well as wielding the most power of influence in the coming decades. And it's not surprising then that you see news about chips and AI, about companies not being able to sell their most advanced microchips to other countries. And to make some sense of all that, we're going to go on a journey through the world of chips. We'll understand how they're manufactured, what this is, and then how we print them on wafers. And at the end, if you want, you can come down and ask questions. I've got some colleagues here who are going to help me out. So let's get started. And so to start, let's ask a very simple question, because we said that we have a fabulous company. What's that? What's a chip? Maybe some of you aren't quite sure what a chip is. And so chips are tiny little circuits, and they're printed on wafers, and this is a wafer. But on this wafer, there's more than 3,000 microchips, and each microchip has hundreds of thousands or millions of transistors on it. And so that's a chip, and a chip gets manufactured in a very advanced factory, and it gets cut up and put into packages, and then that goes onto a printed circuit board, and then that printed circuit board goes into your phone, or your handset, or your car, or pretty much anything that you use today. And they're everywhere. So there's more than 1,000 chips in a modern car, maybe 2,000 or 3,000 of them. When you walk up to your car and you put your hand on the handle, there's a couple of chips in there sensing that your hand's there. They're in your remote control. So when you push a button, it talks wirelessly to the car. They're inside the driver assist systems like ABS and automatic braking. So when there was a chip shortage and we couldn't get one chip for a car, that's kind of why you can't get a car, because every chip has its own function, and it's all very important to the manufacturer to be able to get them. And today's chips are essentially computers on wheels, especially the electronic ones. So semiconductors play a really important role in the transfer of energy from the battery to the motors, as well as the control of the cars themselves. So the companies that are really doing the most advanced software and electronics, so the companies that are the biggest car companies in the world today, like BYD or Tesla, much bigger than the more traditional automotive companies. And those companies make their own chips. And in BYD's case, they actually manufacture their own chips as well. So they're very, what we call, vertically integrated. This is a circuit board, one of the circuit boards from a mobile phone. There's more than 50 integrated circuits inside a mobile phone. And the CPU, the chip that does all of the computing and renders the graphics and runs the software that has all your apps, that's got more than probably 20 billion transistors on it. And so if I highlight some of the chips in a phone, you see the CPU in the middle. That's actually designed by Apple. They're a fabulous company. They design chips. It gets manufactured in a foundry in Taiwan. And there's many other chips on this board. Some of them are doing wireless functions to communicate with the base station. Some of them are doing sensing. So when you touch your phone, they know where your finger is, so they can provide the feedback to the software. And in communications, there's a lot of chips used inside communications. And one example, a really cool example, I think, is a satellite terminal. And historically, satellite internet was geostationary. So you had a fixed dish, and that would talk to a satellite 38,000 kilometers away. And that's great, but there's a lot of latency there because it takes a long time for the signal to get all the way to the satellite and back. And so there's these new networks which have low Earth orbit satellites in them, so constellations of low Earth orbit satellites. And they're only 500 kilometers away, so they're much, much closer. But there's really two problems we need to solve to make a network like this work. The first one is launch. So we need low-cost launch to put all of these satellites up. And I'd argue the second thing is microchips, because you can't have a fixed dish anymore. You need to have a system which can steer a beam across the sky as the satellite's going. And so what we can do with microchips, and you can see how many there are on this circuit board. This is the circuit board from the inside of a Starlink user terminal. If any of you have seen the Starlink internet. And each of these chips is connected to an antenna, and there's more than 2,000 antennas in the system. And the chips are coordinating all of those antennas, and electronically, they're controlling the phase or the delay, and they're able to point a beam anywhere in the sky. And so as the LEO satellites are flying over the head, so they take maybe 4 or 5 minutes to pass, it's pointing a beam on one of them, and then it's pointing a beam on another one. But this is only possible because of the chips that are inside this product. Medical devices, so continuous glucose monitor has a couple of chips in it, one of it for sensing, another for readout and basically communication back to your phone. So this really changes the life for diabetics. You don't need to do finger pricks anymore, and you get a lot more often, you get much faster updates on your glucose levels. And the quantum revolution, you might have heard about this. So quantum's been through a couple of phases. The first is a really deep research phase that happened inside universities where they're figuring out the physics for quantum devices. The next phase that we've had over the last couple of years, or the last 10 years, has been a deep amount of venture capital invested into quantum companies. So they've got a lot of money. And now what they're trying to do is turn these magnificent quantum machines that only have maybe 10 or 20 qubits into them into systems that have thousands or millions of qubits to scale them up. The only way they can do that is with microchips, and with lots of them as well. And the last two I think I have here is one is biotechnology. And so we're really at a point in biotechnology where electronics and bio is coming together. So if we want to talk or understand, read out DNA and RNA, we use integrated circuits. If we want to communicate between cells and electronics, we also need to use miniature electronic circuits. And finally, AI. So AI has really driven a lot of use of microchips, particularly GPUs. You might have heard of a company called NVIDIA. Anyone heard of a company called NVIDIA? Yeah, so large AI models are trained on thousands of GPUs from companies like NVIDIA, and they're distributed across multiple servers. It's estimated that OpenAI has 25 to 100,000 of these GPUs, each of them with more than 80 billion transistors on them. And what's widely recognized now is that these AI models, this current generation of large language models or large reasoning models, scales with the amount of compute you have, and it scales with the amount of data you have. And we're uncovering new data sources, and we're building bigger compute facilities by putting more and more of these GPUs and advanced chips together. And this is leading to an arms race between companies and countries about who can get access to and stand up the largest clusters of these GPUs to train the biggest models. Because they don't just have applications in chatbots, they have applications in national security, they have applications in defense as well. And so all of these systems depend on the chips that power them. And at the moment, for these GPUs, there's only one company that provides them all, and that's NVIDIA. And NVIDIA designs them, like we mentioned. They're a fabulous semiconductor company. All the manufacturing of these most advanced chips is done in a company called TSMC, which is a foundry that manufactures chips, and it's based in Taiwan. And we'll talk more about that a little bit later. But to understand the history of microchips, we're going to talk about two things: computers and semiconductors. And they're both really intertwined, because computers depend on switches, and semiconductors emerge to provide the best switches. And we'll have a couple of technical slides here, but this is as technical as it's going to get. And so the first thing to know is that computers use binary numbers. And they use that because it's really easy. Everything's a 0 or a 1. It's on or off. It's high or low. It's a very easy thing for a computer to understand. And so you can represent that inside a computer as a voltage that's low and high, or a state, a magnetic state if you store something. And then the other cool thing about binary is we don't only use it for storage, we can also use it to make computers. And so what I've got in the middle there is like one of the smallest building blocks of a computer. And we don't need to understand it, we just need to understand that this is what computers are made up of. And essentially, it has two inputs, A and B, and we can put binary numbers into them. And this one, it's a not-or gate, a NOR. You can probably figure an engineer came up with that name. But it says if I put 0, 0 in, I should get 1 out. In every other case, I should get a 0 out. And computers are built up by combinations of many different types of gates like this. But there's one thing here I want you to know, and that's that they all use switches. And these switches are the most important thing inside a computer. If you have a fast and low power switch, you can build these really big systems. And so the first logic gate looks something like this. They took some electromechanical relays out of a Bell Labs telephone system. So these were used to switch the telephone circuits, you know, back when you had analog telephone lines. And so this was a very simple logic gate. There's two inputs at the bottom there, A and B, and they've got the electromechanical switches and then the outputs of the lights. And so they figured out they could do logic with these switches, but they were terrible switches. They only switched 10 times a second. They were power hungry. Because they were mechanical, they would wear out, but they were better than processing numbers manually. And so, sorry for the spelling. Did I spell it wrong? No, it's okay. So then we have a vacuum tube, and that was 1,000 times faster, but it was very power hungry, and it had reliability problems. But because it was 1,000 times faster, we dealt with all those issues, and we made some really good computers with them in the 50s. And that brings us to the first transistor. And this is an interesting part of the story. Transistors are built on things called semiconductors. Now, semiconductors are a very cool material. It conducts sometimes. It's halfway between a very good conductor, like a metal, and a very poor conductor, like a rubber. And we can do different things to semiconductors to make them conduct. So if we heat up an intrinsic semiconductor, that just means a pure semiconductor like silicon here. If we heat that up, it becomes a better conductor because the electrons that are able to move faster, and we can put current through that. We can also do a thing, we can add some impurities to a semiconductor, and that's called doping. And when we do that, we can use the properties to make switches. And that's what Bardeen, Brattain, and Shockley figured out. So they made a transistor, which is an electronic switch, but instead of being a mechanical one, or one that used vacuum tubes, this was a solid state one. So it was potentially a lot more reliable. It was 1,000 times faster again. It was much, much lower power. So vacuum tubes used hundreds of volts to switch, and they generated a lot of heat. This one could run on maybe 5s or 10s of volts. And so the first transistor was really fundamental in building the first kind of no mechanical parts and no vacuum tube computers. Okay, and so what we had in the 50s was computers that were built out of transistors that looked like the little one in that picture there, these 3 terminal devices, and a lot of wiring, okay? And so now the challenge was, how can we take these transistors and make them better? How can we make them easier? And so it was a lot of manual handling to make these transistors. And the first major thing that happened was the planar process was figured out. And that was done at a company called Fairchild by a guy called Hurney. And he made the first planar transistor, and he used silicon. And silicon had this nice property that you could grow this dioxide layer on top of it, which was a really easily to produce insulator. And so the first planar transistor was done in 1959. And now the challenge was, how can we put multiple of these transistors on a chip and then wire them all together? And that was done in 1960, only a year later, by Noyce. And so we say the first integrated circuit was really put together in 1960, and that was multiple transistors in a planar process and wired together with some aluminium. And that started what has been an absolutely tremendous amount of growth. So if we look at a microprocessor from the 1960s, it's not even a microprocessor, it's just a quad gate device. It has 16 transistors in it. And so the first 8-bit processor in the 1970s had 4,000 transistors. In the 1980s, you could get a 32-bit microprocessor with a few 100,000 transistors. In the 90s, 3 million. 2000, 600 million. 2010, 8 billion. Today, 92 billion in an Apple CPU. And this growth has happened every year since 1960. And it hasn't stopped. And we don't know if it will stop, but we don't think it will just yet. And what does process node mean? I don't know if anyone's heard of it, but people talk about 2-nanometer chips and 180-nanometer chips and 0.18 micron and things like this. And so what that used to refer to was the gate length of the transistor. So the gate is the small part of the switch that modulates the current. And since, maybe a few nodes back, that number is really just a marketing term today. So it tracks the node size that you would think, but actually the smallest dimension is not 2 nanometer. In a 2-nanometer process, it's probably more like 10 nanometer. And if I put some process names up against these chips, you can see here, so in the 90s, 350 nanometer process was state of the art. In the 2000s, 130 nanometer was state of the art. And today, a 3 or a 2 nanometer process is state of the art. And probably a better metric to look at when you think about process nodes and technology is how many transistors can I fit in a square millimeter. So a square millimeter is, 1 by 1. And so the density of transistors is probably a better thing to think about. And you can see here, so 90 nanometer was a 2000s technology. So we had about 1 million transistors we could fit in a square millimeter. And then 22 nanometer, maybe 10 million. And today, in 3 nanometer, you can fit between 200 to 300 million transistors in just 1 square millimeter. So just to put that in perspective, in a silicon wafer like this, there's 70,000 square millimeters. So 70,000 times 200 million is the number of transistors I can put on a single wafer. And so back in 1965, this person called Gordon Moore came up with this law. It's not really a law, it's more of an observation. And what he saw was that every 2 years, the number of transistors he could put on a chip doubled. And that has held. And so those dots are examples of chips, and then you see the number of transistors that are on them. And so if we extrapolate that to 2030, we say we'll have 1 trillion transistors on a chip. And so let's see, we're not sure. And just to get an idea of the sizes of things, so we put a silicon atom right on the left-hand side, and then we put a human hair, the diameter of a human hair on the right. Transistors lie somewhere in between viruses and bacteria. So the size of a transistor is 30 to 180 nanometers, a modern one. And then the smallest dimension on a transistor is maybe 10 or 15 nanometers. Okay, so what we'll do now is we'll just go through a couple of things on different types of chip technology. I'm going to talk a lot about silicon or CMOS types of chips in this presentation. And silicon or CMOS chips are 90% of the market. That's the type of process that we use to create CPUs or GPUs. It's what NVIDIA uses to make their fantastic chips. And there's also other processors called compound semiconductor processors. And so they're used in applications where you need maybe slightly better performance for an RF system, or you need better performance for a DC to DC converter. So if you're taking a battery voltage in a car and you're taking it for use in a motor, you would use probably a gallium nitride or a technology like that. And a compound semiconductor is a combination of two different elements. And so silicon or CMOS chips, are primarily based on silicon. And the way chips are designed, and this again is more of a digital design process, there's similar processes used for analog and RF, but in a digital design process, you take some code which describes what your computer should do or your function block, and so we use a high-level language to describe that. So an example is Verilog or VHDL, and we basically use that to describe the functionality that we want the circuit to do. And so I've got a very, very simple example here. I want my output to not equal my input. That little tilde means not in Verilog. And so what happens is we use electronic design automation software to synthesize that code into a schematic to figure out what the transistors to implement that function need to be. And then we take that schematic and we turn it into a layout. So we take the layout and we put the physical transistors and the wiring, and so that's what's on the far right there. And from the very lowest logic block, like an inverter, which is what you see there, that's how chips are slowly built up. And this is an example layout from my fabulous colleagues, Andrea and Jafar, who lended this picture to me for this presentation. And what you see here is the image on a computer of what a chip looks like to a chip designer. Around the outside, you have pads. So they interface with the outside world. So they might be voltage or ground. They might be your input signals. And then we have the green. So that's carrying your power rails around the chip. So it's supplying the power to all of the transistors. And then in the middle, we have all of the logic. So it might be a little CPU. It might be something that's sensing an input from somewhere else. And I put a human hair there on the side. And so what I'm going to do is slowly zoom in, because we're zoomed out to a chip. This might be 2 or 3 millimeters by 2 or 3 millimeters. And if I zoom in, we can start to see the pads there in a little more detail. You can see there's some notes there which say, this is a ground trace, this is a voltage trace. You can see a little bit of definition of the transistors. And then we zoom in again, and you can see something, but we don't really know what that looks like yet. And then we're going to zoom in again. And now if you're into designing chips, you can kind of see some transistors, but it's still a bit hazy. And our hair is, really big compared to the scale of these things now. And we're going to zoom in again, and one more time. And so that's our transistor. And I've put a little 40 nanometer line there because maybe if I can use a mouse. So this is 40 nanometers across there. And so this is a transistor here. And you can see a source and a drain and a gate. And then all these other different colored paths are different layers of metal in that design. And so they might be connecting signals or providing a voltage to the transistor or connecting the circuit up. So that's all the tangle of wiring that we used to have in those computers that were made out of transistors. Now it's all integrated onto the chip. And if we take a cross-section of this, we've got the silicon wafer on the bottom. And what we start with in the manufacturing process that we'll talk about a little bit later is a bare silicon die, and then we slowly build everything up from that. So the transistors first, and then layers of insulators, and then metal, and then we finally get to the top and we can expose the pads, which are around the outside, which we connect to the outside world. And so how do we turn sand to chips? You'd be very disappointed if you came today and the headline was that, and I didn't tell you. So we're going to try and tell you about that, but it's a fantastically complex process. The first thing you need is silicon. And the way we get silicon is we take sand, and sand's made up mostly of silicon dioxide or silica. Okay, and so we take sand, we get silicon dioxide, and then we make it really hot, and we combine it with carbon, and that separates the silicon from the oxygen. So we get silicon and actually carbon monoxide out of that process. And the silicon we get out looks like this. So it's silicon, but it's not in a nice structure that we need to make chips, okay? And so then what we do is we take this silicon, that's bunches of silicon atoms just jumbled up, and we put it into a very hot furnace at maybe 1600 degrees. And we start with the seed crystal that's got the lattice structure of the wafer we want, because silicon's a really nice element. It has 4 valence electrons, so we can make nice lattice structures out of it. Okay, so we put a little chip inside it that's got the right lattice structure, and we slowly pull it out. And I'm going to show a video shortly of that process. But essentially, when we pull it out, we get this big ingot, and then we slice it up, and that's what we start with. Okay, so I'll show a quick video, and this is from TSMC. And so this is the molten silicon, and we've dipped our little crystal into it, and we're starting to pull out and rotate. And it doesn't come out perfect, so we need to polish it and make it the right size, and then we'll cut it up. And so after it's sawn, then we polish it to get a really nice finish. And this is almost, you know, like a mirror. It's so well polished. And so we start with a silicon wafer like this. And the manufacturing of chips is really going through several process stages many times. And so to manufacture the most advanced chips, we take 3 months in a very big factory called a foundry. And we go through maybe 900 different process steps. And these involve depositing either insulators or conductors or different materials onto the wafer, and then applying a photoresist, so a material that's sensitive to light. And then we put that photoresist into a machine called a lithography machine, which exposes, or the patterns are burned into the resist, exposed, essentially like how you'd expose a photo. And then the printer's developed, we etch it and we heat it, and then we maybe put some ion implantation, we take away that resist, and then we do it over and over again. So we're building up the layers of the transistor, then we're putting some insulator down, and then we're putting some metal on, and then we're putting some more insulator, and so on and so forth. And I'm going to show you 2 videos. One is of a, oh, that's not me. And one is of a foundry. So this is a TSMC video again, which shows a advanced foundry. And so the wafers go around the foundry in those pods called FOUPs, front opening special packages. And the yellow light's there because the photoresist we use isn't sensitive to yellow light. And so these large wafers go through many machines and many different process steps, but it's very automated. So there's not any manual handling. And it's, you know, we don't want any dust or any impurities in the process, because if you can imagine how small these transistors are. One speck of dust would ruin a whole wafer. And this is really the hero of the machine, of the manufacturing process. This is the machine called a lithography machine that generates extreme ultraviolet light. This machine is made by one company in the Netherlands called ASML. It costs about $200 million, and it's taken them 3 decades to figure out how to make this machine. And this machine creates the wavelength of light that's so small that can expose these features on the photomask. So the only reason that we can create really small features is because this machine can generate the right wavelength of light that can get down to those small levels. And what we do is we fire tiny drops of tin into the air, and then the first laser flattens them out, and then a second laser pulverizes them to create extreme ultraviolet 13 nanometer light. And so this machine operates in a vacuum because this light is so absorbed by any atmosphere that it would not make it to all the mirrors. And then the light bounces all around and it hits a reticle, which is what the image we're trying to expose on the chip is. And as we're preparing one wafer, the other wafer is getting its image printed on it. And you'll see here in a minute. So this light is exposing the small patterns in the photoresist, and it's doing it chip by chip, wafer by wafer, hundreds of wafers per hour, hundreds of thousands of wafers and multiple machines per month. And this is what we call a photomask. So this is what the light shines through or is reflected from. And you can have a look at it later. It's really hard to see the features in it, but this is what has the tiny patterns. And when you manufacture chips, you need a lot of these photomasks because every layer of the chip has a unique one. The transistors have one, the poly has one, the metals have them. So as you build up the chip, you need one of these, and these are very expensive. So a lot of the cost in the chip manufacturing process, or at least the early engineering process, is in developing these masks. Okay, so we've been through how chips are made. You have a bit of an understanding about what they look like from a cross-sectional point of view. The last step, once you've got your wafer of chips, and I've got one here, and it's probably got a few hundred chips on it. So you can see each of these little squares is a chip. So that will go through a saw, and it will be cut up. So we'll get small little chips out of it. And then we need to package them. We package them because, first of all, we can't attach anything to the silicon. We need to attach the rest of the electronic system to it. We also want to protect it. Silicon's pretty fragile, so we don't want to break it or damage it. And so these are some older packaging technologies. So you've got some inline packages going all the way up to BGAs. You'd see a lot of these in electronic components. If you took your phone apart, you'd see some more advanced stuff. But if you took apart any other system from the last 10 or 20 years, you'd see many, many of these types of chips. Which brings me to advanced packaging. So one of the ways that we're cramming more and more transistors into systems is by putting lots of chips into the same package. Okay, and we do that because we want some really high-speed memory maybe next to a CPU, but we don't want to run it across long distances because that makes it power hungry. And so advanced packaging has really been developed by the CPU and GPU companies. And you can see some examples here. So let's have a quick chat about the scale of fabs. So TSMC's biggest fab, the Giga Fab, projected to do 100,000 wafers per month. And so if we look at it, we've got 70,000 square millimeters per wafer, a few hundred million transistors per square millimeter, and we're doing 100,000 wafers. That's 1.4 e to the 18 or 1.4 quintillion transistors per month. It's just a hard to imagine number. And then let's look at the cost of chips. And I've given a very simple example here. The numbers aren't exactly right, but they're close enough. So if you want an unprocessed wafer, this will cost you $500, say, US dollars. And then we're going to go through that fantastic manufacturing process in a $30 billion factory that we talked about. And after it's manufactured and all the chips are printed on it, it'll cost $10,000. So the cost of doing that manufacturing is added $9,500. And then if our chips are 10 by 10 millimeters, we say we can probably fit 672 on the wafer. Now, some of those chips aren't going to work. They're going to be called defective. And then some of the other chips are going to be near the edge, so they'll be partial. And so we might be left with 500 good chips. So then each chip costs $20. And with all the transistors on that chip, and we can say it's maybe 20 cents per square millimeter. And then we look at the cost of our transistors. So they're very, very cheap. And we look at our plot from earlier. We were talking about the switch cost. So now, with the latest transistors or the switches that we use to do the basic compute unit, we can go up to 5 gigahertz. So we're 1 million times better than our vacuum tube. We're very low power because as these things shrink, the power gets lower too. They're very small, they have great reliability, and they're very, very low cost. But because there's so many of them, they're getting used. And just because transistors have low power, that doesn't mean the systems they're in are necessarily low power, because we have so many now. And so just to go back to this plot, the compute power that's used for AI is doubling every 3 to 4 months. So we talked about Moore's law, and that says that the chip technology will get better every 2 years. This is going way faster than that. That's why people are buying so many GPUs. That's why OpenAI wants to buy 100,000 of these latest NVIDIA GPUs. And all of that compute doesn't come for free. You have to power it. And so here's a plot of energy consumption in the US in terawatt hours per year. And you can see the little uptick in the last 3 years. So that's a real uptick. And then you can see the projections out for the next years until 2030. So power consumption to power these types of systems is very important. And countries that can develop clean and efficient power, can power these systems, can hold the biggest data centers. And that's what a lot of this tension in the world about semiconductors is related to. It's about who gets access to the compute, who can put these data centers together, and who can use them to benefit, the things that they want to benefit. And so, just for the last little part of the presentation, I want to talk briefly about the global supply chain. Chips depend on a truly global supply chain. I think anything this complex, it would be surprising if one country could do it all on its own. And so starting with the raw ingredients, semiconductors use a lot of rare earth materials. Most of these come from China. China also provides 60% of the global annual production of silicon, as well as silicon wafers. Other wafer manufacturers are in the US, Taiwan, Japan, and Europe. A lot of the chemicals come from Japan. The EUV machine that we talked about from that fantastic company in the Netherlands, there's only one provider of that, and that's ASML. And then fabrication of the most advanced chips is done in Taiwan. So 80% of the world's most advanced chips are done by a company called TSMC, or Taiwan Semiconductor Manufacturing Company. China, South Korea, USA, and Europe also have pretty large chip manufacturing industries, but just not quite at that latest node yet. And then the majority of packaging and test happens in Taiwan, Korea, as well as China and Singapore. And so the countries that participate in advanced technology and the semiconductor value chain are the most economically complex. And so economic complexity is a measure of the economy's ability to produce a wide range of sophisticated products and also sell them. And nations with the highest economic complexity often have the most diversified economies and robust technological capabilities. That drives national security and defence. And this plot shows Australia's economic complexity over the last 20 years. So we have a little bit of work to do, but there's a good point here. We can do it. And when you see the headlines, countries around the world are investing heavily in semiconductors. The US announced its CHIPS Act. China's putting a lot of money into it. Europe's put billions of dollars into it as well. And why are they doing this? It's because microchips are the building blocks for all advanced technology. Microchips, AI, and data centers are the infrastructure of today. Everything we do depends on having access to them. And so what can we do here? We can design more chips. We can take part in this great story. We can build data centers, we can host them, we can supply clean and green energy to them. Okay, and we do have some great companies in Australia that design chips. Here's a few of them. And that concludes my presentation. So thank you for coming. I'd like to say thank you for my team who helped me with this. And there's a few of them here tonight. And if you've got any questions, we'd be happy to take them and also talk to you about some of the goodies here. Thank you.
Thank you very much, Mike, for an insightful, inspiring presentation on how to turn sand into chips. We have plenty of time for questions. I need runners for the mics, and I encourage particularly high school students to maybe kick off the questions in case there's one who dares to ask a question.
And I should say I have a prize for the best high school question. Excuse me.
You can possibly start in the front. Just in the front there.
Thank you. As we know that in Australia we don't have a good industry in semiconductor, and we don't have the labor force to supply for the any like a factory for semiconductor. What else we can do contribute in that? Like, we have a good research, but that's it. So what else if we want to develop the semiconductor industry in Australia?
Yeah, I think that's a great question. Thank you. I think we can focus on, firstly, the design of semiconductor chips. So NVIDIA is, they don't have manufacturing, so they just design their chips, and it's a fantastically valuable company with a lot of great technology. So we can build a lot of really great technology without having to manufacture it. But in time, once we've got that large design industry, and once we've got companies that are selling many, many chips, that can encourage some of the foundries to come onshore maybe, like what they're doing in Arizona in the US. So TSMC from Taiwan is setting up a foundry there, mainly because of pull from the US companies and the US government to do that. But they're able to do that because they've got such a large design industry.
So we had a hand up, just up there.
I finished a book called Chip War.
Yes, fantastic.
It's a brilliant book.
Yeah.
And the business with China and its development and how it can't necessarily get its hands on the most advanced chips because it comes from all over the world, different countries are blocking China's import of them. Do you think with the amount of money that China's spending that they'll be able to develop all their own top-end stuff?
Yeah, another fantastic question. Look, there's no question it's fantastically hard. There's no country in the world today that can manufacture these types of chips except for Taiwan. But in time, who knows? Maybe by banning all of these things going in, it makes a country want to be more self-sufficient. So I think it drives to that goal of a country wanting to be able to do it on their own if you don't give them access to technology. So yeah, it's literally an arms race, and it's about who has the capability and the capacity to be able to build these types of technologies. And China's maybe a couple of generations behind, so they can develop pretty good 7 or 10 nanometer chips, but not quite at the 2 nanometer level yet.
So the level of chips that they can develop goes in their weaponry. They've got the elements, the country's got the other bits and pieces. This will equal somewhere, something might crack and they'll be independent.
Yeah, who knows? But yeah, I think it's definitely maybe a goal that they'd be working for, given the environment that the world is in.
Makes Taiwan a bit of a prize for them.
Absolutely, and like Taiwan having that, nexus of basically producing all of the chips, I mean, it makes them very valuable for America to maybe protect, but then China also wants reunification, so, it's a very challenging area.
So we go over there next, and then to the very back.
Does anything have to be removed from the sand before you make it into a chip?
Oh yeah,
Like
all the
silicone?
nasty stuff, all the dirt and all the rest of that, but definitely, yeah. So if you take sand off the beach, there's a big cleaning step, and then you actually need to go through a process to extract the silicon dioxide. And I'm not a chemist, so I can't tell you exactly what that is, but I can find out.
Hello, thank you for the talk. With the Moore's law, or the rapid, just like seemingly never-ending expansion of the transistors you can put on a chip, what could possibly be a limiting factor? Like I've heard sand for glass making is like they're running out of it. Are we running out of sand, or is it just getting more efficient and we need less resources that it could just keep exponentially increasing?
Yeah, great question. I don't think we're running out of sand for chips, but I think we're running to an atomic limit. If you remember the size of the transistor, you know, the silicon atom, sorry, it's like, you know, the spacing between silicon atoms in a lattice is about 0.42 nanometers. And so you can't do anything much smaller than, you know, a few multiple atoms of silicon, otherwise you're dealing with really gnarly quantum effects that won't make a good transistor. So I think the ultimate scaling limit is, you know, a physics question, but then people talk about scaling up. So instead of putting just transistors next to each other, and they do that in memory today, they stack transistors on top of each other. So yeah, I think they've always found a way, but let's see.
Thanks. So my question is related, like we are into the race for creating these chips and we are going with a very fast pace. We see, you know, trillions of transistors getting manufactured. What's the process of reusability of the transistors once we have made it? For example, if I have an iPhone and we are saying that there are so many transistors and chips on top of it, it gets bad. You know, we can't fix it. We can't fix that microchip that's there. So can we reuse it? Is it possible? Can we salvage anything from it, or it's just all done and we are just increasing the, you know, what do you say, garbage basically in the world of semiconductors?
Yeah, I don't know. It's a great question. I think it's hard to reuse. I think the way they're designed and manufactured, it's really hard to take them apart in the first instance, and then to be able to take them apart. And even if you could take a chip off a board, you can't really talk to it without all of the software and the programs that need to go on it. So yeah, it's definitely a challenge. So we need to figure out how to recycle maybe. So I think you can definitely put it through a recycling program, extract some of those kind of rare earth elements that went into it. So I think that's definitely something that people are looking at.
So we'll do 3 more questions.
How long does it usually take to make one chip?
Yeah, great question. So to go through a manufacturer of a kind of leading node, it takes 3 months. 3 months, so it's a very long time.
I was just wondering about the company in the Netherlands that has the lithographic machine, I think. Is there a reason why it's the only company that has it? Is it because of patents, or it's just really hard to produce? And would it be a good avenue for some other company in other parts of the world to increase the global production of chips to start investing in that?
Yeah, great question. I don't actually know, but it's for sure very, very hard. So the technology that they have, like that lithography machine is the size of a double-decker bus. It's a vacuum-based system. It's like $200 or $300 million worth. It's probably the most complex system that humans have manufactured as a machine. So I think, one, it's fantastically challenging. For sure, they've got 3 decades of innovation and learnings and patents around it, I'm sure. So I think it's very challenging, and there's a lot of restrictions on who can get access to that type of technology as well.
Yeah.
So.
Okay. Thank you.
Thank you.
So we go to the last question from one of the youngest members in the audience, and then there's plenty of time after that question to ask questions in the front.
So when the ultralight is made, like what do you need to make the ultralight?
Yeah.
Like what is the ultralight made out of?
Yeah. So the way they make that ultra light is they take tin, which is a metal, and they turn it into a plasma. They hit it with a very high power laser. So the laser pulverizes the tin, and in that process, something that's generated is the light. So the light comes off that, and then it goes through all the mirrors. And I think, I said a high school student, but I reckon you're in primary school. So do you want to come down and get this prize? If you come down, I'll give you this. So this is this is a little pin. You can put it on your shirt, but it's a chip in a package from a company called Silicon Masters. Okay, you're welcome. Thank you.
And on that note, let's thank Mike again and everyone for asking wonderful questions. Please stay back for asking more questions in a smaller circle. I invite you to join us for one of the future Discover lectures. Thanks again for having been here tonight.